Okay, so this is going to be chapter 18, electrochemistry. Now, notice this word right here, electrochemistry. Electro as in electricity or electrons, and chemistry. So you're going to be doing reactions involving typically transfer of electrons, and of course, electricity is actually transfer of electrons through a wire. All right, so right here, that's table of contents, of course. So what we need to start off with is galvanic cells, because that's going to help you build up all your other knowledge of electrochemistry. So a galvanic cell is a device in which chemical energy is changed to electrical energy. Yes, you guessed this right, this would be batteries as well. Uses a spontaneous redox reaction to produce a current that can be used to do work. The reaction will occur at the interface between the electrode and the solution where the electron transfer is facilitated. So if you pay attention and look at batteries, they all have two electrodes, a plus minus, and then in between them, they will have some sort of container in which you will usually have some sort of, almost all batteries have a liquid solution actually inside them. There are a few solid state batteries, but those are fairly rare as it goes. Usually they don't have a huge amount of liquid, but yeah. All right, so galvanic cells, these are examples of a galvanic cell that you can see very easily because we've separated the portions of it, the parts, the cells if you will, into two beakers. Of course, in a battery, these are not separated into beakers. These are actually separated into more contained space. Okay, so right here, this is an example of a galvanic cell with what is called a salt bridge between these. And these salt bridges, they're exactly like their names indicate. So a salt bridge is going to allow the exchange of the ions of a salt through it. It's literally so you can transport cations and anions across here. This right here is a porous disc. This is actually just a type of membrane. So a lot like your cell membranes in SiC, this one is a porous disc. It's more like a wafer of glass usually. It is more similar to that. That's actually what's in all the batteries. That's if you're wondering how they keep making batteries last longer and longer, charge longer and longer. Actually, the development mostly has been in these porous discs and the different components they spike them with. Anyways, galvanic cell components, you have your salt bridge or porous disc. These both are going to act in the same way. You can use one or the other. And these are going to be used to permit ions to flow without extensive mixing, without the extensive mixing of your solutions. Of course, if you mix these two solutions, you'll actually just kill your battery. The reaction, or your galvanic cell in this case. Your reaction would just happen in solution. It wouldn't happen through a wire then. So you need to allow it to selectively mix or to selectively exchange, if you will. A salt bridge contains a strong electrolyte in a U-shaped tube and then usually two plugs at the end to keep that electrolyte from leaking out. A porous disc is going to contain tiny passages that allow hindered flow of the ions. Usually they're size selective, and so the small ions that you transfer back and forth are going to balance your charges, and you would the porous disc would keep your larger ions that you need to stay in each side of the cell where they're supposed to be. All right. Okay, so in all galvanic cells, all of them have an anode and a cathode. Yes, those are those positive and negative symbols on your battery. So the anode is going to be the electrode compartment where oxidation occurs. This right here is your anode. Right here, I'm sorry. I wasn't looking down there when I moved my cursor. Uh, so your cathode is going to be where the electrode compartment where the reduction occurs. And so right here's your cathode. So remember, where the oxidation occurs is going to also be where you have your reducing agent. Remember, oxidation is done um, with your reducing agent here. And your reduction here is going to be done with your oxidizing agent. Notice here that your anode is where you take up electrons. That's why the oxidation is done here. It's losing electrons. And your cathode is where you gain electrons. And so here you're going to have positively charged things typically gaining electrons over at your cathode. One of the ways you can help yourself remember this is at your anode, anions lose electrons. At your cathode, cations gain electrons. That's one of the easier ways to try to remember these. Which of course is oxidation reduction. By the way, this does build off of your previous oxidation reduction or redox reactions that you should have learned back in chapters General Chemistry 1. And these are going to be all reactions where you have one species that's oxidized, one species that's reduced. The oxidized species will always lose electrons. It's going to be oxidized and it is going up in the charge number, which is 2 plus, 3 plus, 1 plus. Those would be the oxidation numbers for a monoatomic ion. All right, and so reduction is, remember, electrons are negative. So when you're doing a reduction, you're gaining electrons because they're negative, right? Reducing. Okay. So cell potential. This is going to be your pulling or driving force on electrons. This is termed as your electromotive force. That's actually an older term for it, and it's actually a better term for it too. So EMF, or electromotive force of the cell. In a galvanic cell, that will be your cell potential. And this cell potential is E as energy. So E for energy. This is literally a force, pulling force, or driving force, right? And this is for the cell. So E sub cell. This is measured typically in volts, which is capital V. That's the unit of your electrical potential. This is defined as 1 joule of work per coulomb of charge transferred. So remember, joule is an energy that you're doing per coulomb. Coulomb is going to be a measurement of amount of charge. Now, this is a larger measurement than an electron worth of charge because these are typically, if you did it by electron, this would be just stupidly large numbers. You would never be able to actually write them down easily. Now, all of you should be at least moderately aware of voltage or volts. And yes, those are the electromotive force that you're talking about. So when you're talking about a 120 volt socket that you have in your wall, that's what you plug in your computer and everything else into, that is actually this volt right here. You are specifying the electromotive force, the EMF, on that socket. And literally what you're actually looking at there is the best analogy whenever I think and talk about electromotive force is a waterfall. So think of your wire as a little hose. And I find that electricity is, you've probably worked and played with hoses before and, squirt guns and pools and everything else, right? Waterfalls. You have more hands-on experience with that. You probably don't have a lot of hands-on experience with electricity. And hopefully you don't have much of all hands-on experience with electricity because it is a shocking experience. However, when you think about electricity, the way I want you to think about it is the wires are like little tubes, okay? And so electromotive force is best thought of like a waterfall. So at the top, where you have a lot of electrons, you have a large amount of electromotive force, okay? At the bottom, that difference between that top and the bottom of the waterfall would be your electromotive force. That is the amount of force moving those electrons. Just like the gravity is the amount of force moving that water down the waterfall, right? And so if you hook a wire or tube, right, at the top of a waterfall and then go down to the bottom of the waterfall, that water is going to have a certain amount of force. And that's what they use water towers for. Water towers are literally towers they pump water up to the top of. And then if the electricity goes out or you don't have anything to pump water with to keep your mains pressurized, you will slowly drain that water tower to keep all the water flowing. That's literally what you're doing with water, okay? You're doing a very similar thing. It's just that instead of height, instead of gravity, that's electromotive force you're talking about. And so when you talk about a power plant, for example, it has a series of wiring that's going to come out from it. And I'm oversimplifying it, to be fair, but it's a good oversimplification. So at the power plant, they have 120 more volts of potential energy of electromotive force difference at that power plant than on the line that comes back to that power plant after it hits all your houses. Okay? And that difference in the electromotive force, that's going to cause a certain amount of electricity to move through that wire. And again, that is 1 joule of work per coulomb of charge, which we'll do watts in just a bit, in case anybody knew a little bit about electricity already. Okay, so when you use a voltmeter, this is a way of measuring the cell potential. So a voltmeter draws a current via a known resistance. Essentially, it's like measuring against something. If you measure against a known amount of resistance, you can measure the force to overcome it. The maximum cell potential, this can be ascertained by measuring it under zero current. The potentiometer. This is a similar concept, but it's a little bit different. So a potentiometer will have variable voltage device. Which is powered by an external source. A voltmeter usually doesn't have an external source of power. Voltmeters actually can be run just off of the electricity you hook it up to measure. A potentiometer will always have an external source of power, whether that's a battery hooked up to it or whether it's hooked up to the wall. This is inserted in the opposition of the cell potential. And thus it can therefore very accurately measure the potential of the cells of like a battery. This is a great device to measure a battery. Here's a digital voltmeter, by the way. You can actually get them very, very small now. Here we see that we have our galvanic cell hooked up to this, and it has a cell potential, or EMF, of 1.06. That's the difference in the force between this and this cell. Okay. The following two half reactions take place in a galvanic cell. At standard conditions, which species are produced at each electrode? Alright, so what you want to look at here is you have these cell potentials over here, and you need to get a positive cell potential overall for this, okay? So this value already is positive. You need this negative value to be flipped. Another way you can think of this is a larger positive number, and so you need to flip this one so you have something to strip electrons away from, right? Because we see that this one's energetically favorable to take on electrons. Many of you probably could have done this just by looking at copper versus tin. Copper is going to take up electrons better. Tin will lose electrons. And you could have done that from the previous General Chemistry 1, where we looked at the activities of these. But I want you to be able to do it the correct way, which is the cell potential should be positive overall. And that's going to give you that is right here. This is fine. We don't do anything with this copper reaction. That's in the correct direction. This one should be flipped. And so what we should be doing is, instead of reducing copper like it's doing right now, we should be oxidizing. I'm sorry, this is not copper. Tin. We should be oxidizing the tin instead of reducing it like it's being shown right there. So if you flip this, that will flip this sign right here. That will give you a positive overall cell potential. And that means we are producing tin 2 plus, which will go to our products, and we are producing copper. And so it is E. Again, how do you know the anode versus the cathode? So remember, the anode, you are going to be oxidizing, so that means you're removing electrons and they're getting more positive. The cathode, you're going to be reducing, that means it is going to be going more negative. So the one that's more positive, that you're gaining positive charge, is always at the anode. The one you are losing positive charge or gaining negative charge is at the cathode. All right. And given these half reactions, which of the following is the strongest oxidizing agent? Okay, so again, an oxidizing agent is going to be taking electrons away from something. And so what we're looking for is something that's really good at taking electrons away from stuff. And so here, this is really good at taking electrons away from something. So it has a large E0 value here for this reaction, which is taking electrons. See that? It's using electrons. This right here has a negative value for taking electrons. So that's obviously the exact opposite of what we're looking for, isn't it? And so yes, it is MnO4 minus that is very good at taking electrons, and so it's a strong oxidizing agent. And actually, that's a pretty strong oxidizing agent just overall, not just strongest of these. It's a strong oxidizing agent overall. Notice, by the way, one of the options was MnO2. Be careful. This right here is a strong oxidizing agent. This, on the other hand, would be a weak reducing agent. It'd be the opposite, wouldn't it? Because you would be giving electrons to go to that. All right, so which of the following is the best reducing agent? Of course, it's the same sort of concept before, we're just doing it in reverse. And so what we're looking for is something that easily loses its electrons and reduces the other thing. Remember when you're talking about agents, agents don't kill themselves, they kill other people, right? And so a reducing agent does the reducing to something else. All right, now, sodium here has a fairly large negative value, and so we know that this reaction is going to prefer going this direction, which means losing electrons to something else, or reducing something else. Determine the standard reduction potential for the following reaction. And we got that reaction there. Following are the standard potentials. Okay, so we're looking at zinc here is gaining electrons to go to the metal. And notice that this same species are showing up right here in this reaction. But we have a silver that's riding along with us, don't we? So we need to deal with this silver somehow. And we need to flip this reaction so these species are on the same sides as what we're trying to look at. And so the first thing we can do is we can flip that, and that will be a negative value right there. Now the next thing we can do, and we'll need to do, is our silver here, that's going to be on the correct side, the Ag plus an electron right here, right? And then Ag. That will help us cancel this, the silver and the Ag silver salt. And so what we do is we don't take any difference in the sign, but we do have to add these together once we flip to this. And that will give us negative 0.76, because this was a negative value. So minus 1.56 once we flipped it. And then we added 0.8. Now, one of the things that catches a lot of people out on this is that they go to me, Dr. Clausen, we did all these Hess's problems, we did all these a delta G, delta S, and all of these, the coefficients here changed these values, didn't they? So if you need it, so you would think that you need to do this twice, don't you? 2Ag plus, and yeah, you do. You do 2, 2, 2, and that would give you this reaction. But, okay, so, sorry about that, false start. Okay, so this question right here, many of you may be wondering why this is not being multiplied by 2 across all of this. These are multiplied by 2, even if you have to multiply these by 2, which you do here, because there's 2 silvers in this, and you need to match that 2 silvers, so they cancel properly. And then this 2 electrons, you need to match in there, so you have to have 2, 2, 2. Now, you never multiply these E naughts, and I'm going to explain it in using scientific terms first so that you can first off understand how to use scientific terms and where they apply. And then I'm going to explain it with an analogy. So first off, these are intensive properties. And you remember, intensive properties mean that they don't change depending on how much you have. They're inherent to that system or an inherent property to that substance. And so these don't change depending on how much you have here. They'll stay the same no matter what. The opposite of that being extensive properties. Extensive properties will change with how much you have. And that example of an extensive property is, of course, heat, right? Or enthalpy changes. So the more gasoline you light on fire, the bigger the flame will be. If you burn a drop of gasoline, you're not going to get a lot of heat, right? Or enthalpy. If you burn an ocean of gasoline, you're going to really get some serious heat. And of course, that's your enthalpy, right? So in these cases, the analogy I want you to think of is, again, think of that waterfall, right? And so what we were looking at was the height of the waterfall. That's that potential right here. Now, will the water come down any harder if you keep that same height for the waterfall, but you make it 20 kilometers long? No. The water won't come down any harder than it did before. It won't come down with any more force. However, if you shrink it and make that waterfall very narrow, it also won't change with how much force that water will come down with. And so that won't change your potential energy here. It'll just change the number of electrons you move, right? So that's your best analogy here, I think. That overall covers it quite nicely. The only thing that matters for potential energy is the potential energy, is which waterfall you're looking at, right? Are you looking at a very tall waterfall, or are you looking at a very short waterfall? Are you looking at something that has a lot of potential energy, or are you looking at something that has a little bit? And that's what determines your EMF. And that's why you don't have to multiply. You never multiply your EMFs, okay? Careful, please remember this. Get it some way that sticks in your head, because this is the number one most common mistake that I see in these problems by far and away. Usually, if people study at all on this and have any idea what's going on at all, the one thing they miss is this stuff, where they try to multiply these E naughts by whatever number they're multiplying this stuff. Because you get used to it, right? We've been doing all this stuff where we multiply everything through. When we put coefficients in front of these, they have some sort of effect on the K. They have an effect on the delta H, the delta S, the delta, everything else, right? Just here, no. They have no effect on the E naughts at all. You just do this, and you have your E naught here. The only way you can affect your E naught here from this is the direction. Are you going up or down? All right, so standard reduction potentials. E naught values will correspond to reduction half reactions. Excuse me. Had a weird false start there. Just couldn't get my words out. All right, so your E naught values. These are going to be all corresponding to reduction half reactions. You're always going to be in the reduction. So that means you're always going to be adding electrons to a positive charge, and they're all always going to be listed like that. So if you look up E naught values, they'll all be the reduction half reaction. They'll never be the oxidations. And how do you get the oxidations? Well, you just flip them, don't you? You flip them so that the electrons are coming off instead of going on. Now, all of the E naught values also have a standard set concentrations and pressures for the gases. And that is that all solutes are 1 molarity, and all gases are 1 atmosphere. And so all the concentrations are set concentrations for these E naught values. All half reactions are always given as the reduction process in standard tables. You can, however, look up specific tables where they list the oxidations. Those do exist, but there's really no point in them. I have no idea why somebody thought that was necessary. Because you just flip them. So right here we see a standard table for these half reactions. Notice they're all in the reduction, so all the electrons are on the left in the reactants, and you are gaining electrons for all these reactions. If you want the oxidation, again, you just flip this reaction and flip the charge. So this will be a negative, that would be a positive then for the oxidation. Okay, and so these right here, this is another way of representing E naught. It's this cursive E character that you will see in many of the older tables. Honestly, most of the newer ones just drop it and call it E naught cell or E naught, whatever. They're in volts, of course, because that's the unit you measure all of these in. And all of these are for 298 Kelvin, which is room temperature. Notice, by the way, that yes, these do relate back to the equilibriums and the energy, the delta G's that we talked about before, and we will go over how those relate. So the temperature does matter, okay? Concentrations and temperatures both matter for these. This is more of them. There are many half reactions you can get. You can build complete reactions by simply adding half reactions together until you get the overall reaction. You may have to multiply the entire thing through with a factor or coefficient, right? So you may have to do 2, 2, 2, something like that. You may have to flip these. You will definitely have to flip one of these when you build a complete reaction, because typically you are not going to see half reactions in most solutions that you look at. The exception for that being when you look at our galvanic cells we looked at before. That's actually why we have the two different sides. One is for the reduction, one is for the oxidation, right? And so literally we've split our half reactions apart in galvanic cells. So obtaining a balanced oxidation reduction reaction, we're going to have to do some manipulations here. When a half reaction is reversed, the sign of E naught is of course reversed. The E cell for a galvanic cell is always going to be the E naught of the cathode minus the E naught of the anode. You really don't need to memorize this per se, as long as you understand what happens at the cathode, what happens at the anode. So at the cathode, you have a reduction. So you have what's going on right here. So you don't have to change the sign. At the anode, you have a oxidation occurring. You have electrons coming off instead of going on. And so you have to flip all the signs. All right, so when a half reaction is multiplied by an integer, E naught will stay the same. It will remain the same. The standard reduction potential is, of course, an intensive property. And I'm just restating that because it is very important. It's one of the major ways I see people mess this up. The redox reaction right here, this is a redox reaction, redox meaning reduction, oxidation reaction, or an oxidation reduction reaction is actually the correct way of saying that as a full term, or redox reaction is fine. Now, this is iron. Iron is going down in its positive charge. So iron here is gaining an electron, isn't it? Whereas copper right here is losing electrons. And so our copper is being oxidized, our iron is being reduced. And you see, literally, the number here is reduced. So the half reactions that we're looking at for this overall reaction is iron 3 plus gaining an electron to go to iron 2 plus. This has an E naught of 0.77 volts. And we also have copper 2 plus gaining 2 electrons to go to copper metal. There's the copper metal, there's the copper 2 plus right there. Here's the iron 3 plus, here's the iron 2 plus right there. And that's how you can tell those. And again, this value just comes from that table. Notice we have again listed these half reactions as the reductions. So when we try to balance the cell reaction and calculate your standard cell potential, you have to reverse this second reaction right here because we have copper on the reactant side. So we need to flip this like so. And so we have flipped it. We flipped the sign so it's negative. Remember, you don't have to do any multiplication. And we now have to multiply the reaction of the iron by 2 because you will see that this is just that restated the reaction of the copper that we flipped. This is the iron. We have multiplied it by 2 now. The reason we need to multiply that by 2 is there are 2 electrons. So we need to have our same number of electrons on both sides. So they will cancel. You will notice there is no electrons being shown in this overall reaction. Okay, so now our number of electrons are the same on both sides. They will cancel, leaving us with the iron and the copper. Notice that that accounts for all the electrons, though please, again, look at that. We have not changed that from multiplying this by 2. That doesn't change that. All right, so we then add those together. That will give us our copper metal, 2Fe3 plus, copper 2 plus, and the 2Fe2 plus that we saw from the overall reaction before. To get the cell potential, we're again just going to add these two numbers together. If you do it like this, where you're actually writing out the half reactions and getting them fit together to form the overall reaction, you literally just have to add these because you've already done all the signs, right? You've already taken care of that. But if you want to make this faster, so you don't have to do all this work, if you just want the E not cell, then what you can actually do is you can just look at our values here and you can go, well, this right here is in the correct direction. This one is in the reverse direction. So it's going to be this minus this. And there you go. That will give you your answer, which is 0.43 volts. Again, that is cathode minus anode. Or another way of saying that would be your reduction minus your oxidation. All right. Let's consider a galvanic cell based on the following reaction. So here we have this reaction here. I'm just not going to say it. I'm dying here. My voice is starting to go. All right, so our half reactions, we looked them up on the table. Again, Al3 plus right there, Al right there, Mg2 plus, that's from right there, Mg from there. And so we have now accounted for all of our metals there. Okay, so we obviously are going to have to give a balanced cell reaction, and then we're going to calculate the E naught for this cell. When we do this, we are obviously going to have to flip this, and we're going to have to get these number of electrons so that they equal for both sides. All right, so let's go ahead and do this. Our half reaction involving the magnesium, this has to be reversed, right? Because that's an oxidation. That's the anode. And so we flip our magnesium. That means we have to flip the sign too. So we make that, we go negative, negative, and that will give us an overall positive value. Since the two half reactions involve different numbers of electrons, we have to multiply these by integers, so we have these same electrons on both sides. And so to get them to be the same electrons on both sides, we just cross multiply. So this is a 2, this is a 3, you multiply the top by 2, you multiply the bottom by 3. Notice again, we don't do anything with these. I'm going to say that's the last time, okay? Hopefully you have it by now. Our cell reaction, therefore, is going to be 2 Al3 plus, 3 Mg, 2 Al, and then 3 Mg2 plus. Notice again, we don't put any electrons here because our electrons will cancel. We have 6 here, 6 here. Our E0 cell is going to be negative 1.66 plus 2.37, which is 0.71 volts. All right, so line notations. You may have noticed that writing out these reactions can be a bit of a pain in the butt, and writing out a galvanic cell, therefore, needs something faster, easier to do if you're going to have a bunch of notes you're taking on different batteries you're testing, or you're going to work with this at all. So line notations is a quicker, easier way to do this. It's going to describe the electrochemical cells. Your anode components are always listed on the left. Your cathode components are always listed on the right. One of the ways you can remember this is anode is A, that comes first. Cathode is C, that comes last. So left to right, just like you read. The other way you can think about this is your anode here, that's always going to be your reduction, and your cathode is always going to be your oxidation. And so your redox, right? Just like a redox reaction. Okay, so the anode and cathode components are going to be separated by double vertical lines. The double vertical lines actually indicate the salt bridge or the porous disk. It literally indicates a separation between the two cells, which is your salt bridge or porous disk. And in fact, it kind of looks like a porous disk, so that works nicely. The phase difference boundary is going to be indicated by a single vertical line. Now, what am I talking about for the phase difference? Look, that's a solid. That's aqueous. Those are different phases. So that was the phase difference, okay? You may have one wondering why there's all these plates of metals connected by wires in those beakers. There's your plate of metal. It's something to plate out this solid magnesium. Or on the other side, plate out the solid aluminum, right? And then the aqueous components are, of course, going to be dissolved in that solution that you saw filling up the beakers. So this is a great example of this, of course. Mg solid, and of course our aqueous component is Mg2 plus. You can tell that this is, so you can see here that our anode here is being oxidized, and that is what an anode does, right? Okay, so remember, folks, the anode is where your oxidation occurs. The cathode is where your reduction occurs. Did I get that backwards when I did this? Shoot. Anyways, remember, anode comes first, cathode comes next. The easiest way is A, cat. Okay? A, then C, right? Now, the anode is always where your oxidation occurs. Your cathode is always where reduction occurs. So in the anode, the first one that comes up, you're always going to go from the more negative component to the less negative component, because that's oxidation, losing electrons. At the cathode portion, you're always going to go from the cation to the anion, or the more positive to the less positive. So you're gaining electrons at that side. Okay, And there you go. Notice the singular lines, phase boundaries, double lines, porous disk, or salt bridge. You should always go ahead and list the phases that these are in. They don't just have to be aqueous, solid. They can be gases. You can have a variety of different things, actually. And the component that's important for all of these are always the species that is actually being reduced or oxidized. Okay? So magnesium here is what's being oxidized. If you have more than one species in this, the one that matters is the one that's actually losing electrons and the one that is gaining electrons. All right, so the cell potential and the balanced cell reaction. The cell potential is always positive for a galvanic cell. And the reason that is that it needs to provide some sort of electricity. So it needs to be positive so that the flow of electrons is from the reduction to the oxidation to the reduction. Man, I'm backwards today. I guess maybe I am. If you're familiar with Bizarro from Superman, I guess I'm Bizarro Dr. Claus and everything's backwards today. All right. So your cathode, again, is your reduction. Your anode is your oxidation. So this is, of course, you're putting off electrons at the cathode, which are then being... I did it again. I'm getting enough tea in me that I'm starting to wake up again. Okay. Reduction happens here. Oxidation happens here. So at the oxidation, at the anode, you're going to be taking electrons off. Those are going to be moving to the cathode, which is your reduction. Okay, so keep that in mind whenever you look at these things. The direction of your electron flow, this is of course obtained by inspecting the half reactions and using the direction that gives you a positive E0 cell, so your electrons will actually flow in the correct direction. Think of it like this: if you did this the wrong way around and you were making a galvanic cell, it's going to be a battery for your phone. Instead of providing power, running electricity through in one direction, in the correct direction, it would actually run it in the reverse direction. Now, that may not seem, if you know a lot about electronics, that may not seem that bad, but the last time that happened to a computer that I hooked up to a wall, somebody had actually wired a plug-in in my home I just bought, reverse. So the positive was on the wrong side, the negative was on the wrong side. And it literally shot sparks out of my laptop, maybe buy a new laptop, 6-7 feet, and it gave me a hell of a shock. So it really actually does matter in any digital device or anything that's a little more sensitive. However, it doesn't actually matter for analog devices, interestingly enough. So this is going to give you that designation of your anode and cathode. If you messed this up and you did not get a positive E0 cell, you'd actually have these swapped around, which would be like putting your battery in backwards. It's actually what you're doing when you put your battery in backwards, by the way. The nature of each electrode and the ions present in each compartment. If none of the substances participating in the half reactions are conducting solids, you are going to have to use a chemically inert conductor. Think about it this way. Some of those reductions that you saw in that standardized table of half reactions, some of them had things like hydrogen gas they're making, right? How in the world are you hooking up any type of wire to a gas? I think about that. That doesn't make any sense. And so, sure, you're doing one side with platinum solid, you're doing one side with copper solid. Those will work fine, right? You can just use the copper and platinum for your electrode. You can hook your wire up to it. Great. Awesome. Might be a little on the expensive side, but still. What you do on the other side, though, if you're doing something like H plus going to hydrogen gas on the other side, which is actually a very popular experiment to do in these. That's one of the ways you can make hydrogen gas, by the way, for like hydrogen fuel cell cars. Okay, so you can't use hydrogen gas as your conductor. It's not a conducting solid. It's not even a solid, it's a gas. And so what you do is you would typically use something like a rod of platinum, or you can actually make a certain type of graphite conductors. They're fairly chemically inert as well. But most of these are actually platinum. And if you noticed, I talked about before, you may be picking up hints now that, remember the pH probes I talked about before? Well, that actually works through this same sort of phenomenon right here. That's an electrode inside that glass ball, if you look at it very carefully. And typically that is a platinum electrode actually. And that's one of the reasons why they're so expensive, is platinum's quite expensive itself. Okay, so let's look here. This is a description of a galvanic cell. So describe completely the galvanic cell based on the following half reactions under standard conditions. So, since a positive E0 cell is required, reaction 2 has to be run in reverse because you need an overall positive value. Remember, one of these has to be the reduction, one of these has to be the oxidation. And so the one you flip, so that it is now going to be the oxidation, always has to be the smaller value, so that the overall E0 is positive. And so we flip the iron, and that gives us a negative 0.77 to subtract off. That would give us an overall cell reaction of this right here, which is the silver ion is taking on an electron, give you silver metal. And that would give our overall E0 cell a 0.03 voltage charge. By the way, yes, that would be a very low potential. That would not be what I'd recommend to, make a battery out of. But this could be great for getting some silver, solid silver out of it. So Ag plus is going to receive electrons. Fe2 plus will lose the electrons in this cell reaction. The electrons will flow from the compartment that contains the Fe2 plus. This will flow to the compartment containing the Ag plus. The oxidation occurs in the compartment containing Fe2 plus because the electrons again are flowing away from that compartment. This compartment therefore has to be the anode. The oxidation occurs at the anode. The reduction occurs at the Ag plus compartment. That therefore is the cathode. So our electrode in the silver compartment, silver would be perfect. Okay, it's inert. It's not going to be reacting away and doing strange other reactions that we don't want to deal with, because it already is silver. So it's already just going to be involved in this reaction we're looking at. It's also quite conductive. It's a great conductor, actually. Okay, so the other side, we will have to use a platinum conductor. And the reason for that is iron is actually not a very good conductor. It heats up very easily when you pass electricity through it. It actually has a fairly high resistance. And so if we were to try to do this reaction through an iron conductor, we would end up heating the solution around it. We may even boil some of the solution away. Okay? And that would change things a lot because it changed concentrations, temperatures. We'd be in a lot of trouble. And so you would usually use something like a platinum probe here in your iron part of the galvanic cell. Excuse me, I hit the button there. Oh, let's see if I missed anything. Alright, so the appropriate counterions are assumed to be present. What appropriate counterions are is something like nitrate. Okay, so you would have nitrate that can move back and forth between these and act as the negative ion to cause this to not build up a positive charge on one side or a negative charge on the other. Okay, So that's literally what we're talking about when we're talking about those salt bridges and what they're doing. They're allowing a counterion to move across so you don't build up a positive or negative charge on one side, which would, of course, halt your reaction and make it so it doesn't work anymore. The line notation for this is going to be, so when you do these line notations, again, remember that single line was the phase boundary. And so our platinum conductor that we're using on the iron cell side, this is going to be that solid, platinum. And that's going to be our electrode on that side. Then we have a phase boundary, and Fe2 plus aqueous going to Fe3 plus aqueous. The other side, separated by our porous disc or salt bridge, is going to be Ag plus aqueous, phase boundary, solid Ag. And this is what it would look like. We have our anode, which has our excuse me. All right, so we have our anode here, which we are stripping electrons away from. And that is that oxidation where we're going from iron 2 plus to iron 3 plus. And again, that's our platinum probe right there. By the way, this is not normally like solid sheets like this. Usually this is a bit more like a strip. It's not quite that big usually. Anyways, you can use a fairly big one, but that'd be a very expensive probe. You're probably talking like an $80, $100 probe at least. Anyways, you're moving electrons then through here. That's indicated by a positive 0.03 voltage. Remember, this is higher potential, lower potential. That's going down the hill. And then this is going to have electrons going along this silver plate. And that silver plate is actually part of that half reaction right here. See that? So that silver plate is part of the half reaction. And this is literally going to have these silver ions here gaining electrons, becoming solid silver. By the way, you would actually expect this platinum plate would usually stay pretty clean. You wouldn't expect any buildup on it or anything, or any weird stuff to occur. But the silver plate here will actually gain mass. It will gain more silver. And that's because you have solid silver plating out on it. Now, typically this solid silver does not plate really nice and even. And so you will typically see either striations, sort of like a tree where it's, a little wavy looking, or you will see a sort of spongy surface start to develop on it, which is literally silver making sort of wires off of it that sort of curve around and make sort of this sponge or steel wool looking thing. Okay? If you're curious. Anyways. So work and cell potential. So your cell potential E, that we've already been talking about that. The work, this has opposite signs to your cell potential. So your cell potential here equals negative work over Q. Or the negative work equals QE. Now, W max, work max, maximum amount of work you can do, is equal to negative Q times the E max, the maximum cell potential you can have. So these are directly related. They are proportional to each other. In any real spontaneous process, some energy is always wasted though. So you never actually get a full usage out of this. You're always going to get some of it wasted. So actual work realized is always going to be less than what you calculate here, this calculated maximum. The actual work done is given by this following equation here. So E is the actual potential difference at which current flows, not this E max, right? And Q is the quantity of charge in coulombs transferred. Now I know this is very confusing that we've used a Q here. Frankly, this is something that work was done on it, and work was done on the other thing, and nobody really communicated when it was first done. And so these both were set, and they have a long history past. So Q, you're probably used to this being heat. It is not heat when you're looking at these, okay? Q is the quantity of charge that you have moving around here in coulombs. So that's the quantity charge in coulombs that you transfer. All right, so we need to discuss a Faraday because now we're getting into coulombs and quantities. Faraday is the charge on 1 mole of electrons. So a mole of electrons has 96,485 coulombs worth of charge. So this is the Faraday right here. You will notice it is a kind of weird, it is a very weird number, right? 96,485. It's really quite a bizarre number. And the reason this happened is moles of electrons really didn't have anything to do with coulombs of charge. Coulombs of charge they came up with that from measuring a certain amount of charge, and they didn't even really know that there was electrons, that was something to do with electrons. They had no idea at the time. And electrons were, people found out about electrons and much, much later, decades and decades afterwards. So there really wasn't any way this could have been a nice number. But I do list it off in that periodic table I give you for every exam. It is something that you would typically be able to get access to. So potential and free energy again. So change in free energy equals the maximum useful work that can be obtained from a process. So W max actually is equal to delta G for these. So for a galvanic cell, we can see that W max is equal to that negative Q, the charge being moved, right? And E max times E max. This same relationship, W max, also equals delta G. So we can set these two things equal to each other. But first, let's get rid of Q, because that's a pain in the butt. So let's replace that with instead Faraday times the number of moles, which will give us that charge being moved. And so we see that delta G equals negative NFE. And that's E max there, which is usually what you end up calculating or close enough. So we see that the free energy difference here between the reactants and products in your cell is actually directly related, it's proportional to your cell potential. And that is actually quite a nice, interesting thing, right? That means we actually can do a lot of work. We can measure cell potentials and get, hey, delta G of a reaction. That's kind of cool stuff. The galvanic cell will run in the direction that provides a positive E cell. So remember, this E cell, positive E cell, means it runs spontaneously in that direction. And why does that do that? Well, that gives you a negative delta G, doesn't it? There you go. That's why the E cell has to always be positive to run spontaneously in that direction, moving electrons in the correct direction. And that's why if you get this reversed, if you were to give a negative E naught, that would give you a positive delta G, and that would mean electrons would run in the reverse direction spontaneously. So positive E cell is going to imply a negative E delta G value. And again, that is the condition for spontaneity. You will also notice, of course, if you have an E naught of 0, that would also give you an equilibrium, wouldn't it? So when we use the data in table 18.1, we can calculate the delta G naught for this reaction. And we can find out if this reaction is spontaneous. So our half reactions are these. Notice we flipped this one around because this one is the reduction, this one is the oxidation. Again, this is the cathode because that's reduction. This one's the anode because it's the oxidation. All right. By the way, one of the easiest ways you can sort of help yourself remember this is I always remember the cathode starts with a cation, okay? Because it's going to be taking up electrons to reduction, it always starts with a cation, cathode. Cats are positive, right? All right, so here we have 0.34 minus a negative 0.44, which gives us 0.78 volts for this overall reaction, our E naught cell. We can plug this into this equation right here. And so when you look at this, you may be going, what is this N? Which one do I select for this N? Well, you're talking about moles of electrons here, right? So the N is always the number of electrons. That, right there. Which you have to make equal to get your overall reaction, don't you? And that's why I was stressing to make those number of electrons equal before, because that right there will give you your number of electrons in any of these calculations. So this will be a 2 here. That comes from right there. So you have the 2 moles of electrons. The F Faraday is going to be this 96,485 coulombs per mole of electron. And if you remember what an F is, moles of electron, that will give you a big hint on what you use for this N, which is moles of electrons, right? All right, this E naught is that value we just calculated, 0.78. And so you may be wondering that 0.78 volts, why is that used? How does this work for units? Well, a volt is a joule per coulomb, right? So when we multiply this E naught, we're multiplying it by coulombs on top, which means the coulombs cancel. That will leave us with joules. We have moles E of electrons, which is going to be multiplied by moles of electrons here. And so this denominator cancels the numerator here. And that will leave us with joules overall. Joules are energy, which is the same thing that a Gibbs free energy is. Notice the name, Gibbs free energy. So we plug all these in, these cancel, this cancels, leaving us in joules. We will go ahead and do the math real quick, and we get a negative 1.5 times 10 to the 5th joules. So this process is spontaneous. That's indicated both by a negative sign on the delta G and a positive sign on the E naught cell. This reaction is actually used industrially to deposit copper metal from solutions resulting from dissolving of copper ores. This is one of the ways you can get copper metal on an industrial scale. For any galvanic cell to operate, well, the delta G must be negative and the E naught must be positive, right? They have to be spontaneous to operate. So, for the cell reaction right here, predict whether E cell is larger or smaller than E naught cell for the following cases. So remember, when we look at these E naught cells, these were always for 1 molarity for all these concentrations. And so, a higher molarity would indicate to you, if you think back to your Gibbs free energy and everything else you've done, well, higher molarities would indicate that you're going to end up changing that E cell for those conditions, right? By the way, you will notice E cell does not have naught here. The E naught cell is for those standard conditions, remember? That's for that 1 molarity of every solute. That E cell is for whatever conditions you actually have, which is these right here. Okay, so right here we have aluminum 3+, that's in the products, and we have Mn2+, which is in the reactants. And so we have 2 molarity of that, 1 molarity of that for A. For B, we're going to have 1 molarity here, which is the same as the standard condition, right? And 3 molarity there. Okay, so let's try this out. A product concentration has been raised above 1 molarity. That's one we need to focus on. So this is going to oppose your cell reaction according to everything we know about equilibria, which is like Le Chatelier's principle, right? We have increased the concentration of product, therefore it's going to push towards the left, which is the opposite direction of E cell, isn't it? And so you would expect your E cell to be less than the E naught cell that you have calculated. So E cell should be less than that 0.48 volt value. When a reactant concentration has been increased, well, that's going to push it towards products. That means you're pushing towards E cell. You're making that value larger. And so E cell will be greater than E naught cell. And your E cell, therefore, will be greater than 0.48 volts. You guys may have already realized a little bit, but yes, the delta G, where we set delta G equal to natural log Q, yes, that is going to show up again. Yeah. We're seeing these same relationships, aren't we? All right, so concentration cells. These are going to be cells in which both compartments have the same components at different concentrations. So instead of having something like silver and iron, you could have silver nitrate in both sides. So you have the exact same salt on both sides. You have the exact same half reaction on both sides. The difference will be in the concentrations, like the name of them, right? Concentration set. And so at your anode, you'll have a lower concentration here. And at the cathode, you have a higher concentration of this half reaction. This causes you to have different E cells on both sides, doesn't it? Because you have a lower concentration here, the electrons are going to move from this side to your cathode here that has a higher concentration. And so the cell potential is a factor of the difference in your concentrations here. Typically, the voltages for these are fairly small. You can get a much larger voltage by doing appropriate half reactions at each side. These are typically much smaller voltages. Now, your concentration cells are determine the direction of electron flow and designate the anode and cathode for the cell represented in the figure. We're going to go ahead and try to do this little problem here. And so on the left, good grief. Anyways, I have labeling here that says anode and cathode, but we're doing that. All right, so on the left you have a 0.01 molarity iron 2 plus. And then this is your solid iron right here. That's your half reaction then. And we're trying to figure out, are the electrons going to flow away from this to here, which has a 0.1, 10 times the concentration of iron 2 plus, or will they flow from here to here? Okay, so the concentration of iron 2 plus ion in the two compartments can eventually be equalized by transferring the electrons from your left compartment to the right. Okay, I'm going to show you the math behind that in a bit, but I always like to point out the logical way you can do this, that many things can actually be deduced just by pure logic. All right, here you have 0.01 molarity of Fe2 plus. Ultimately, what you want is to consume one of these to make both sides equal. And to consume, well, you don't want to consume this, right? You want this side to come down to equal this. So what do you have to do to this side? Well, you have to give this side electrons, don't you? So that the Fe2 plus will go to Fe. And so you know that the electrons have to move this direction over here, from this side to this side. Moving electrons from here will cause this Fe to go to Fe2 plus, and that will come over here, cause this Fe2 plus to come down, and cause it to go to Fe. And so that will cause these two sides to become equal eventually. But let's go ahead and look at this. Okay, so we know that the concentration of the Fe2 plus ion in the two compartments can be equalized by transferring the electrons from your left compartment to the right. This will cause your Fe2 plus to be formed in your left compartment, and the iron metal will be deposited, which is what I just said. I gotta have my notes, didn't I? So the electron flow is going to be from left to right. The oxidation occurs in your left compartment, so that's your anode, and the reduction occurs in your right compartment, which is of course your cathode. Again, your electrons always flows towards the cat. One of the ways you can also remember electron flows, and I don't know why I didn't tell you this before, because I didn't have enough tea in me, is, okay, so if you have ants and you have cats, where do you want to give stuff to? Well, you always give it to the cats, right? Everybody likes cats. Nobody likes ants. So the electrons always flow from the ants to the cats, okay? That's one of the ways people tend to remember this better. Nernst equation. So this is going to explain the relationship between the cell potential and the concentration of cell components. This is going to be based on that same equation we saw before. You can actually see the parts of this a little bit if you remember what delta G equals negative NF. you can start seeing it a little bit, can't you? Anyways, here we have this Nernst equation. E, so that's going to be your cell potential at those given concentrations, at the given conditions, equals E naught, those are under the standard conditions, minus RT, remember the temperature plays a factor, divided by NF. These two are both constants. R and F are constants. This is the Faraday. This right here is your universal gas law constant. And of course, is just your number of electrons. Okay, don't forget it's the number of electrons. It's not some moles of iron or something like that. This is one of the things people get freaked out about all the time and send me questions about. Where am I getting moles of iron or moles of whatever, right? It's moles of electrons. All right, times the natural log of Q. And yes, that's the same Q, reaction quotient or ion ratio, same Q as you've done all those other times. So we can actually simplify this relationship for 25 degrees Celsius, which is lab conditions, room temperature, where most of our reactions end up taking place because we won't watch them or use them for a phone or something, right? So E equals E naught, same as before, minus, we have taken this F, R, and 298 for this T. We have combined it into a single term here, which is 0.0591. You don't actually have to memorize this. If you can solve this, it's not a problem. Divided by N, which is again our number of electrons, times the log of Q. Again, that's that same reaction quotient you've seen before. So the resulting potential calculated from the equation is your maximum potential before any current flow. As the current flows, this is going to become less and less and less. Because remember, eventually you are going to get an equilibrium state. Once you have had all your current flow and the two sides will have the same concentration, that will go to equilibrium. And in equilibrium, you're not going to have any spontaneous flow in the other direction. So, a cell will spontaneously discharge until it reaches the equilibrium. That means Q equals K, which is your equilibrium constant, right? The E cell at equilibrium will be 0. And so, at equilibrium, your E naught is going to equal, this is that 25 degrees Celsius one, by the way, 0.0591 divided by the number of electrons, moles of electron, times the log of K, K being at equilibrium, right? Equilibrium constant. By the way, notice that this conversion right here, this 0.0591, This actually includes the conversion from a natural log to a log, if you're wondering what's going on. That's why that's a log there. Okay, so a dead battery. This is going to be a battery in which the cell reaction has reached equilibrium. So your battery dies and becomes less and less effective the closer you get to equilibrium, right? And when you reach equilibrium, your battery will be completely dead. You can't get any flow of electrons anymore. At equilibrium, both cell components have the same free energy, and so your delta G will equal 0. So you don't have any spontaneous flow or spontaneous reaction. The cell can no longer work at equilibrium. It's a dead cell, it's a dead battery. Okay, one of the things I would like to point out right now, this concentration cell, people always ask me, what is this used for? Why does this exist? What's going on here? There's not a huge number of applications for people. There's a few. These are things like some of the little fun batteries you can make at your own house are concentration cells. But probably the most well-known example of a concentration cell is the electric eel. And that actually operates, the electric eel stores up a higher concentration in its cells. It then releases it, and that causes a voltage discharge. That's actually a concentration cell. That's how the electric eel actually works. So, okay, let's try an example where we use this Nernst equation. So describe the cell based on the following half reactions, where T equals 25 degrees Celsius, and then we have these different concentrations. Notice that this and this one correspond up here. This right here corresponds, of course, right up there as well. And that concentration right there is Zn. Right there. Why don't I need any concentration for Zn here, the solid metal, or H2O, the pure liquid? Again, these don't actually have concentrations, right? They always go to unity. So if you have a pure solid or pure liquid, they always go to unity. Again, this is an application of that same equilibrium constants that we learned before, that same reaction quotients that we learned before. So the balanced cell reaction is obtained by reversing reaction 2 and by multiplying reaction 1 by 2. So we multiply by 2 on this one, we reverse this one, and that will give us our balanced cell reaction, like so. Again, notice that this again is going to give you a positive E0 cell. So our E0 cell is 1.76 volts. Again, that is E0 cell, which is the little degree symbol right there if you forgot. All right, so the cell contains components at concentrations other than 1 molarity. So we're going to have to use our Nernst equation. For our Nernst equation, N is going to equal 2 because that comes from those 2 electrons right there. See, the 2 electrons that we had to equal out. So at 25 degrees Celsius, we can go ahead and use the simplified equation right there. So we have to plug in less stuff. So we go ahead and plug in our E0 cell, our 2 right there, and then we have our concentrations here. Again, where do we get this? Well, this is from that complete reaction. So Zn2 plus had a coefficient of 1, so it's going to be to the first power. This right here has a 2, so that's going to be to the second power. These are products, they're on top. This one and this one are on top. That is a pure liquid, you don't have to put it in. This will be divided by concentration of H plus to the fourth power, concentration of VO2 plus to the second power, right? And again, that is that same Q reaction quotient, which is just like doing a an equilibrium expression that you've done so many chapters now, so many problems. Hopefully at this point that's like breathing. Hopefully generating one of these is just, boring to you. Breathing, whatever. I've done it already. Okay, so You plug in your concentrations, take them to their powers. This is one of the places where I honestly, I probably get a good 70% of the people that fail these questions that just fail them because they do the damn calculator wrong. They don't plug in things with parentheses in the right places and etc. What I would highly recommend when you do these, do them piecemeal, do them step by step. So square this first, take this to the fourth power, take that to the second power, rewrite it, do the multiplication, rewrite it. Do the division, rewrite it. Log that, rewrite it. And just do it step by step, honestly. Because I see so many students fail these problems and they really just don't need to. They did the hard part, they just can't seem to get their calculator to work right for them. Careless mistake. And so we go ahead and simplify the problem a little bit. We do our math, and we get 1.89 volts. And you can see that due to our concentrations, we actually have a greater voltage than we normally would, which is nice. Alright, so this is just an exercise problem that you could have verified that you understood this, but you guys don't really need that because you have your problems throughout. So determining ion concentration, the cell potentials can help determine concentration of an ion. We have voltage differences that will be above or below a standard cell, don't we? So you can do things now where you take a standard cell, measure if it has a voltage that is going away from it or coming to it and how much that voltage is. And that's going to tell you whatever you put it in, whatever you're exchanging electricity with, whether that has a higher or lower concentration than the half cell you have in your probe. Okay? And this is how a pH meter actually works. So this is going to be a device used to measure concentration using observed potential. You'll have a standard electrode of known potential. This is literally a half reaction that's contained inside that tube. So it is actually an H plus gaining electrons typically to go to hydrogen gas. That's what it is. It's just that half reaction, that known half reaction. This is at the standard concentrations typically. You have a glass electrode then. The charge potentials based on H plus ion concentration in a solution. And so your glass electrode can be used to exchange one ion between whatever you stick it into. Then you have a potentiometer that's hooked up to the top that's going to measure how much voltage is moving, how much the voltage changes when you stick it in there. And so right here you see our, well, this is an actual pH meter here. This is just a, cut out of it. So right here you see the glass membrane right down here. And here you can actually see the electrode here. Typically this is a platinum electrode. And you can actually see the solution in here as well, which is your reference solution of dilute hydrochloric acid. That's going to have that typically 1 molarity of H+, but you don't have to have 1 molarity of H+. You could calibrate it. Usually you have to calibrate it because the solution amount in here oftentimes gets messed up due to being old, right? The reference solution, of course there, you can do a silver wire coated with silver chloride to reduce the cost. That's typically a little bit less accurate. The platinum ones are better, but whatever, they're usually good enough. And of course, this is a very thin glass membrane. That's one of the reasons it breaks so easy. It has to be a thin membrane. If it was too thick, you would have to sit there and wait for hours to get any measurement for your ions to migrate through. So the thinner this is, the faster this will work. So electrical potential will depend on your difference in H+ between the reference, which is here, and the solution which you dip your electrode into. This will vary with the pH of the solution being tested because, again, pH is just a measurement of concentration of H+, isn't it? All right, so you can also make this for other ions. You don't have to just do it for pH meters. You can make these for all sorts of ions. In fact, there are hundreds, perhaps even thousands, of different probes available on the market. And this is actually something that has experienced somewhat of a renaissance lately. Um, there was sort of a absence of work done on this back in the 1990s and early 2000s. And then computerized, computers got really small. And so you could now make chips and ion selective electrodes that were extremely small on very small wafers that are very, very sensitive to voltage changes. And so they literally make these ion selective electrodes now and they print them onto wafers as if they're computer circuits. And you can have all these tests now on this little tiny wafer like the size of your thumb. And it's quite amazing what has been done with this in the last like 10 years. This has really just exploded. And many of the quick diagnosis tests you've started seeing showing up, they're used more in the third world because they're very cheap, and the accuracies for a lot of these are just not as well proven yet, or just not quite there. So they need more time to, make them a little bit more accurate, make sure they have the statistics of how well they do on detecting negatives, false negatives. So you typically see these more in the third world or when you need emergency applications of this. But these are actually becoming quite ubiquitous. And I've seen the most, probably the coolest one I've seen is an HIV test that's 10 cents to make. So that was pretty cool. All right. Anyways, you'll probably see these more and more. I would guess in like 20, 30 years, you will see these as the primary testing method. You probably will not go to a medical professional to get most testing done. You'll just get shipped one of these, and there you go. You put a little blood on it, whatever. And you may not even have to put blood on it if it's designed correctly. Anyways, some great examples of this. These are a bit older examples, but they're just good examples. They work nicely. Using a crystal of lanthanum 3 fluoride, LaF3, in an electrode to measure F minus. You can use a solid silver sulfide to measure Ag plus and S2 minus. And so these ion selective electrodes, you're going to have an electrode that are sensitive to the concentration of any specific ion because they're going to have a half reaction at known concentrations in that electrode. Right here, these are some of the ions whose concentrations can be detected by ion selective electrodes. This is just a very small selection. Honestly, it's really a huge field. It's an amazing field. If you ever want to get into something kind of cool, this would be a great field to go into. And you can do this as a biochemist, as a biologist, medical professional. This is something that actually is just ubiquitously useful. All right, so right here we have some of the cations that you commonly will see these ion selective probes for, and they're anions right here. And you can mix and match a lot of these actually. Okay, so the calculation of equilibrium constants for redox reactions. So you notice that the equilibrium constant actually was related to your cell potential. So E naught and delta G naught have quantitative relationships. You already knew that the equilibrium constant was related to delta G naught. So at equilibrium, E cell equals 0, Q will equal K, and so we can just substitute those in, 0 and K. And of course this is for 25 degrees Celsius. So we go ahead and get all these other terms on one side. So you're left with log of K on one side by itself. And you see this relationship right here, which is the log of K equals number of the moles of electrons times E naught over that 0.0591. So let's go ahead and try this out a little bit. So we have that reaction up here. We have the two half reactions here. Balance the redox reaction. Calculate E naught and K at 25 degrees Celsius. And so the first thing we do is we go ahead and figure out which side is the cathode, which side is the anode. Of course, this value right here was positive, while the other value was a negative. So this is going to stay as a reduction, the cathode. This other one has to flip so that we can get a positive value from it. And that means that is the anode, because that is an oxidation right there now. We need to get our number of electrons equal, so we multiply this by 2. One last time, we multiplied this by 2, so do we do anything to this? No, because that is intensive. Does not matter how much we multiply this by. Okay, so now we add those two together. We cancel off our electrons, and we're left with this cell reaction right here. That will give us an E naught of 0.67 volts, which is this, plus the negative times negative, this. Okay, so we have 2 electrons. Again, where do we get that? This number right here. So our 2 electrons is going to be our 2 moles of electrons transferred for each round of this reaction. So for every 2 moles of Cr2 plus reacted with 1 mole of this S4O6 2 minus act, that will form 2 moles of Cr3 plus and 2 moles of S2O3 2 minus. To do this reaction, every cycle of this reaction, we have to move 2 moles of electrons. So the N equals 2. And we substitute that 2 in, we substitute our E naught in, and we can solve for K. So the log of K will equal 22.6. How do we get rid of that log? Well, we do the anti-log, which is 10 to the power of that number. So K, we take 10 to the power of on both sides. K will equal 10 to the 22nd, 0.6. And that will give us 4 times 10 to the 22nd. This is an extremely large equilibrium constant that really isn't unusual for a redox reaction, though. Many times, these redox reactions will actually have very large equilibrium constants. They will greatly favor one side. And that's actually why you experience many of the things you may have experienced if you did the activity series, any sort of labs with the activity series back in General Chemistry 1, where you added like HCl with a metal, and you saw that it dissolved the entire metal. And you added copper to a metal ion, and you saw that, copper completely plated out. If you added copper metal ion together with magnesium metal, you saw that the magnesium was completely consumed, while the copper ion actually was converted to the copper metal and left there. That's why these happen to such a great degree, why they favor one side so completely. All right, so for any operating concentration cell, well, E naught must be 0 and E must be positive, because remember, the E naught is going to be the same on both sides. We have the same cell on both sides. We have the same half cell on both sides, right? We have the same half reaction. So that E naught from the table is the exact same. But the E, not under standard conditions, the E, which is dependent on our concentrations, right? That has to be positive. So in a given Cu copper concentration cell, the concentrations are 0.01 molarity copper 2 plus and 0.1 molarity copper 2 plus. In which direction will the electrons flow? Well, they're going to flow from the low concentration to the high concentration of the ion, the cation. Again, the way you can easily just remember this is that what you want is to put electrons onto this so that your ion, your cation here, goes down in concentration by forming the metal. And thus, these two concentrations become the same. All right, so a battery. Batteries are typically going to be groups of galvanic cells that are connected in a series. And a series means one after another, so their potentials will add together. Potentials of each individual cell will end up adding together to give the total battery potential, which you typically don't want a battery with, 0.5 volts or 0.3 volts. That wouldn't work as well. So what you typically want is like a 9-volt battery, right? That's something you typically see, a 9-volt battery. Um, so you want to add these together one after another to chain them in a series that will give you a higher potential overall. Much like you could stack waterfalls to give you more energy when the water hits the ground, right? The essential source of a portable power in today's society is batteries. And interestingly enough, it is one of the primary things that's necessary to make renewable energy a reality. Solar panels simply do not give you power all the time, especially at night. So, you need batteries to store that energy. The types of batteries. I'm only going to cover these types of batteries. They're the most common types of batteries that, and the most concerning to you. Lithium-ion batteries is probably the big one you guys actually know. It's the one that's in your computers and in your cell phones and Tesla cars. And there's actually various different types of lithium-ion batteries that have various different additives and slightly different structures. And it's had a huge boom over the last 30, 40 years. But there's just so many types of batteries now that I'm only going to cover these. Okay, if you want to know more, you can send me an email. You can take some sort of advanced course on this. Honestly, there's just too much. I could easily teach a class just on lithium-ion batteries. I could teach a class over that, and I'm not even a professional in that field. Um, anyways, lead storage battery. Typically these days, this is most commonly used for a power grid, especially like city power grids. This sometimes is also could be found in cars, especially old cars. Old cars only had lead storage batteries. So the components of these is your anode, which is lead, your cathode, which is a lead coated with lead dioxide, and your electrolyte solution, which is sulfuric acid. If that sounded dangerous to you, yes. Yes, it is. This is a liquid sulfuric acid with wafers of lead and lead dioxide coated lead. The electrode reactions will be this right here. So here's your anode, which is your lead right here, going to the lead sulfate. That's why you have that sulfuric acid, by the way. And giving off an H+, which again, notice these are both things that are from the sulfuric acid. Okay, so your cathode reaction is then going to be this, which is your lead oxide. Again, notice that is the deprotonated sulfuric acid. H pluses, which again are from the sulfuric acid. And right there's your lead sulfate. You will notice that when you look down here, your lead sulfate is actually a solid here. Okay, so right here, this shows you the wafers of your lead and your lead oxide, your anode and your cathode. In a lead storage battery, you would typically have 6 total cells, and that's actually what, if you look really closely at many of the lead storage batteries, you can actually kind of see them. Oftentimes, they'll sort of almost have an indent or some sort of indicator on these 6 cells. Anyways, what you'd see here is here you have your rail that's going to carry electricity. These are all going to be attached to your anode around this direction, which is your negative. And over here, your positive is attached to your cathodes. And you'll have a rail down here that's attached to these green wafers. Okay? And so what you're going to see here is this H2SO4. This is actually your electrolyte solution. it's also acting as your salt bridge. Now, when you see a lead storage battery, there's two main things that happen here. First off, these wafers. I know they look a bit like pancakes here, but they're more accurately described as a grid filled with a spongy lead. Um, they're like a structure that then has sort of a lead sponge in between each one so it doesn't collapse and they don't hit each other. Okay? Your sulfuric acid here, if you leave this car out under the sun, you will have the water that is dissolving the sulfuric acid will evaporate. And that can leave you with solid sulfuric acid down here, or at least a very, very concentrated slurry down here. And this battery will stop working then. And what ends up happening is this is why there's a little cap here. You can unscrew the cap and you can actually pour water in here. Or you may have to take off the top to pour water in, depending on the design. Anyways, this actually used to cause a lot of problems, and you used to be able to see people that worked with cars a lot, and a number of them would have like burns on them. And the reason for that is that people would try to fill up their water here to get their battery to work again. And if you're not careful and just pour the water in on a hot day, this can cause the sulfuric acid to splash back up at you, and it can get you in the face, arms, and burn you really badly. If you've ever seen what sulfuric acid does to people, it turns your flesh into sort of this black goo. It's pretty nasty. Anyways, you will see here that this anode, this is marked with a negative. Our cathodes are marked with a positive. One of the ways you can sort of remember this is anode, negative. Cathode, positive. If you remember, your anode was giving off electrons, and that's where the electrons come from. And so your negative here is actually your live, it's where electrons come from. By the way, that's always the dangerous one. That's the one that actually has a buildup of electrons. That's the one that can actually electrocute you to death. Your positive one, actually, the potential energy, if it's large enough, could harm you, but it's a lot harder for you to actually die from it. Usually it just causes things like you can have a tremendous amount of potential energy applied over you. That's how Tesla did those demonstrations he used to do, which you can find videos on YouTube of. They're pretty cool, where he would actually like throw lightning bolts out of his fingers. He'd apply a potential across himself and a wire mesh that he would wear. And it's kind of a cool thing. Anyways, you can look it up sometime. Anyways, there you go. There you got some general idea. Dry cell battery. Here's the acid version of this, which you can probably say, hey, there's probably a base version later. Components. You have a zinc inner case that will act as your anode. You have a carbon rod that's going to contact with the moist plate of solid MnO2. You'll have solid ammonium chloride and carbon that will act as your cathode. So right here's the anode reaction, that's that zinc casing. So you have your metal zinc giving off electrons. At the cathode, you have this reaction right here, which is a little more complicated. You have the NH4 ammonium, MnO2 gaining electrons to give you this Mn oxide right here, this Mn2O3. This has this cell potential, by the way, not that that really does anything for you. Okay, so you notice we don't bother really showing this. The acid version, as far as I'm aware, isn't really as used as much. The alkaline version is the one you guys probably know and love. Those are the alkali batteries, or alkaline batteries, that you can pick up from the store. So if you look at the supermarket, right next to the cash registers, there's always the alkaline batteries. This is what they're talking about, actually. Alkaline is in base. So these have ammonium chloride. We replace that with the sodium hydroxide, or KOH, potassium hydroxide. So again, the anode reaction is the same. But the cathode reaction, again, has the MnO2 going to Mn2O3, which is so similar. But in this case, it's going to produce OH minus, a base, instead of water. See that? And so this is going to last for a longer period of time because the zinc corrodes less rapidly under basic conditions. The You really don't see the acid version very much because these would corrode very, very quickly. Every now and then, if you get a very cheap alkaline battery that you put it in and all of a sudden it's gone, it's corroded, not just running out of power, but completely corroded within a couple months, that might have been an acid one. But the alkaline ones last a tremendous amount of time, years and years and years. I'm pretty sure, I think if I remember correctly, that there's been ones that have lasted a decade. So these are typically what you see at a store because you need these to not corrode quickly. The store has to actually keep its stock, right? It can't afford for a set of batteries to stay on its shelf and it's corroded after a month. They may not sell all their batteries after a month. So these take a very long time to corrode. And if you've ever had a battery corrode, and I've had a number of batteries corrode. I've only changed the batteries of my calculator once in 30 years. I was given this calculator in elementary school, and I still have that same calculator. Anyways, that same calculator, I changed the batteries once, and all the batteries that were in it, the only reason they died was because it was corroded. And there was white powder that was in there in the cavity where the batteries are located. And so that powder is actually basic. That is actually your basic slurry of this MEN2O3, zinc oxide, and then some of this base, NaOH or KOH. And so if you want to get rid of that, there's actually a very easy way. You will notice that all of these are hydroxides or oxides. So all of these will become more soluble in the presence of an acid. So if you just take a little bit of lemon juice or vinegar, mix it in with a little bit of water, and take a Q-tip or a paper towel, you can actually use that to dissolve all of that white gunk. And I actually helped somebody fix a $700 watch once because it had one of these alkaline batteries that went and it just filled the entire inside workings of a watch and gunked it up, and you couldn't do anything about it. All you had to do is just take a little bit of lemon juice with some water and soak the watch in it for a day or two. There you go. It will dissolve all of this stuff and you're good. You're gone. Congratulations. By the way, this will turn you into soap very slowly. That's called saponification because this is a strong base. So if you ever get that stuff on your fingers, do not wipe your eyes. This is the common dry cell battery that we talked about before. And so this right here is your anode, that zinc inner casing we talked about. Typically you would surround it with some sort of like a tin or something else, which would be for structure. That's that copper top, if you will, or the little patterned metal that they surround it. Sometimes this can be like steel, very low grade steel, whatever. It's just to keep it from, breaking, because zinc is not that strong. This right here is your cathode, which is the inner graphite rod, and that's actually going to be what connects up here. Right here then is your paste with the MnO2. It really is a paste. If it's the acid, it has the NH4Cl. The base has the KOH in there. So silver cell and mercury cell batteries. These have almost completely been phased out. Frankly speaking, silver, first off, silver's expensive. Mercury isn't exactly cheap. And mercury is quite poisonous to the environment. Silver is actually not good for the environment either. Silver causes a lot of damage if it's in its ionic form to life forms. Anyways, the silver cell, this contains a zinc anode and a cathode that uses Ag2O as the oxidizing agent. They're very similar to the dry cell batteries that we saw before. They're just... Oh, by the way, I know this looks like the full battery. A typical battery actually would be, this cell would be much smaller. It would only be a little tiny puck. And they would stack a multitude of these on top of each other in a series. And that's your typical AAA, AA, whatever battery, D cell, whatever battery you're talking about. And they actually standardize these and make these pretty much the same for all of them. And they just stack a certain number of them to give you your voltage. Anyways, mercury cell. This contains a zinc anode and a cathode that uses mercury oxide as your oxidizing agent. These are really quite terrible for the environment. If you get one of these and you have to dispose of it, please do so properly. You can take it by Walmart and they can help you dispose of it. Also, you really should do that for your lithium ion cells as well. So your lithium ion rechargeable batteries and such, you should do that for that as well. So here's a mercury type battery. These used to be what they put in watches, and you can still find them every now and then. Though these days, frankly speaking, there were higher power output, voltage output for size. They are pretty much gone now. Lithium-ion batteries just has taken over all the rechargeable, non-disposable battery usages. It's pretty impressive, actually. And they made them a lot cheaper over the years. They've done a great job. There's a lot of developments that have happened with lithium-ion batteries. So nickel cadmium batteries, this is again one that you'd typically find for like a watch battery. You can still find nickel cadmium batteries. They were a type of rechargeable battery at one point. Anyways, this is the anode reaction right here, which has cadmium. This right here is your cathode reaction, which is nickel. And your lithium ion batteries, of course, this is for the one you guys probably are more interested in. This is really the battery tech these days. Lithium ion batteries with various other additives in them are being used for pretty much everything now. So in a lithium ion battery, this works pretty differently than these other batteries. The lithium ions will migrate from your cathode to your anode. You actually pass the lithium ions through your salt bridge. It's actually a membrane, but you get what I'm talking about. It's a electrolyte membrane. It's kind of a different thing. They use a more advanced version of a salt bridge. And so these lithium ions will migrate from your cathode to your anode when it's discharging power. And they will enter the interior of the battery as it's charged. So what you do is you then, when you discharge, migrates from the cathode to the anode. And when you are recharging it, you migrate it the other way. So this charge balancing electrons will travel to the anode through an external circuit in the charger. So it has an external circuit which you move the electrons through to help you move the lithiums. The opposite process is going to occur on your discharge. All right, I don't have a graphic for that day. Anyways, that gives you a good enough understanding of lithium-ion batteries. An interesting side note, and I get asked this almost every class, Dr. Clausen, can you tell us a little bit more about lithium-ion batteries? Because it's honestly, it's something you guys are using so much, right? And actually knowing something about it actually is helpful. And so yes, I will tell you a little bit. I've actually read the Battery Doctor reports for this, and they do a series of testing on these to find out what the best conditions and everything else about lithium-ion batteries are. And so some of the things that I can tell you that might help you in life is don't let a lithium-ion battery get hot, especially if you're charging it. So if you charge a lithium-ion battery and it is warm, hot, especially don't let it actually get hot. So if you're charging it, do not leave it under a window or next to a fire or any of these things. Lithium-ion batteries, if they are hot while you're recharging it, you will make lithium crystals. And lithium is actually very reactive to moisture in the air. So if you make lithium crystals, it will break the outer shell around the lithium ion battery, and it can actually light on fire. And that's where you heard of like those galaxies bursting into flames, or those hoverboards bursting into flames, or any lithium ion battery bursting into flames. Yes, that can happen, especially if you recharge it when it's hot, because lithium crystals are quite explosive actually. And yes, lithium ion batteries are in themselves um, are actually incendiary devices. This is one of the reasons why they're always scanning your phone and your computer, because the lithium ion battery is actually explosive. That lithium ion battery, if you pay attention to the box you get your next phone or computer in, your laptop in, then you will actually notice a sticker on it that shows a person like running away from flames or shielding themselves from flames, and a little like do not cut in, do not stab with a knife. And the reason they're telling you that is if you stab and break the outer shell in a lithium ion battery, it can light up, and it can light up pretty fast and can cause you burns. Um, One of the other things, can I overcharge a lithium ion battery? No, no, you can't. The only danger you have from overcharging it is if it gets hot. If it gets hot, then yes, charging it's going to cause problems and it'll cause damage. That's swelling. If you ever notice an old phone starts like popping open, swelling is actually due to you making lithium ion crystals, typically because you charged them as hot. You will notice that your phones, actually the newer phones, typically actually like run their fan when it's charging quickly, and that's to keep it cool. Let's see. Lithium ion battery is actually your most dangerous thing. You do never want to discharge a lithium ion battery. If you discharge a lithium ion battery to completion, this will actually destroy its lifetime. It will actually cause it to last less time. So you never want to completely discharge it. Lithium ion batteries, your number of cycles of charge discharge, that's not actually what matters. What matters is the amount of complete cycles. So let's say that you charge it, you never let it get below 50%. That's not going to negatively impact the life of your battery at all. The lithium ion batteries will uh, really, it won't matter at all. If you discharged it all the time, that would impact it. But let's say you use it to 75% and then recharge it all the time, you can continuously do that too. It won't matter. Your battery that you discharge 50%, the battery you discharge 75%, those are going to last the exact same amount of time of usage of that battery, which means the exact amount of electricity that each of them provided to those devices. It's really the percentage overall that you've used of the battery for its entire life that matters. Okay, I think that probably is enough. I hope it's enough. If anybody wanted any other specific questions about lithium ion batteries, I actually know quite a bit about them. More than I really want to know, if I'm being honest. Anyways, let's get on. Fuel cells. This has become a pretty big topic recently because there's actually a number of companies that have already produced working fuel cells and have deployed them across the world. And there's even car companies and truck companies that are working on producing hydrogen fuel cell vehicles. So this is a really cool thing that's starting to gain a lot of traction. So galvanic cells for rich reactants are continuously supplied are called fuel cells. So all a fuel cell is a galvanic cell that you keep feeding reactants to and taking away the products. So right here, this is a hydrogen oxygen fuel cell. This is the basic overall concept of what you'd see in a hydrogen fuel cell car. Frankly, the individual concepts, I don't know. They're proprietary. I don't know what's going to actually get put in a car. So I have a kind of an idea, but I could be completely wrong. Uh, but this overall one tells you enough that you'll get the gist of any of the hydrogen fuel cells. So right here we have the anode reaction, which is going to be H2, which you continuously feed in. This will react with hydroxide ion in this fuel cell right here. The cathode reaction is going to be electrons being uptaken by O2 and water. And this will again give you hydroxide ions. And so what you get here is electrons moving from your anode here, which is the hydrogen, to the oxygen over here. And these electrons moving are going to power that, like a water wheel on a river, right? That's how electricity works. Remember, I want you to think of wires as like rivers or like hoses, right? So your tire or engine or whatever will be connected in here, and our transmission, I guess, would be the more accurate. Um, Really, they're a type of electromagnetic engine or a electromagnetic motor, if you're talking about flying a drone or something. Anyways, you move electrons through the wire from here to here, from anode to cathode, and you have a motor or whatever in between, and that's going to cause that motor to run. This right here, this is actually one of the major places development's been happening on these. So these are usually something like a porous carbon electrodes that contain various different catalysts. And that's about as accurate as I can give you, because I mean the shape of this is going to be changed for each different manufacturer, and well, honestly, this basic shape is good enough for you to understand. And this part is the magic part right here. This catalyst combination and this usually porous carbon electrodes. That's really your magic part. That's where they do their magic, and they have their proprietary technology, which there's no way they're gonna let me. Well, I do know a few people's, but I can't tell you. I'd be sued. The ones I do know really are probably not their cutting edge either. So, eh. Okay, so this is also the process of corrosion. So when we talk about corrosion, like rusting, this can be viewed as a method of returning metals to their natural state, or iron oxides. Those are what most metals are in their oxide forms in nature. So the natural state are going to be ores, which the metals are originally obtained from, and those are typically oxides of some sort. This involves the oxidation of a metal. This is a spontaneous process because oxygen uptakes the electrons much better than the metal. Some metals tend to develop a thin oxide coating to protect against further oxidation. Aluminum is a great example of this. If you've ever had any aluminum surface or aluminum container, then you will notice when it gets scratched, it gets very shiny. And that's actually showing you what aluminum looks like. Aluminum is actually very shiny. So the aluminum that you see normally, that's that dull color, that doesn't oxidize very quickly, that is a very, very hard, thin layer of aluminum oxide, which is this Al2OH6. It's very hard, very resistant to reaction, and so that protects the aluminum inside of it from being oxidized further. And that's why aluminum typically is not oxidized very quickly, is really just because of the aluminum oxide layer. Actual aluminum is oxidized usually in a matter of minutes, tens of minutes usually. Copper forms an external layer of the greenish copper, which is the carbonate called patina. Most people don't realize this for one reason or another, but Lady Liberty is actually copper. She should be this like beautiful reddish burnish color, and she's green instead. And that's because over time, after the French gifted her to us, she developed a copper carbonate patina, and that has protected her from further oxidation over the years, uh, though they did have to do a bunch of restoration something like 10 years ago. Or maybe it's 20 years ago now. I don't remember. It was when I was young. Now I feel old if I'm not considered old. Anyways, so silver sulfide, this is going to form silver tarnish. This is that sort of black tarnish you see on silver objects. Yeah. Okay, so this is the electrochemical corrosion of iron. And this actually explains why, if you've ever paid attention to rust, you'll notice the part that's actually in the water actually is usually not that rusted, doesn't have a huge buildup of rust. It's usually the part that's at the surface of the water that has the huge buildup of rust, or somewhere nearby, because water goes up and down due to the tides usually, or waves, either one. So what you're seeing here is an iron object. This water droplet is going to be where you have your anodic area, your anode. And so the iron is going to dissolve, forming a pit. And that's the damage you usually associate with rusting. Pitting, right? And the dissolved iron is going to travel through the water droplet, and that's why the water is so important to rusting, is if the water wasn't there, the iron wouldn't be able to go anywhere. So you just develop salt right here, and it wouldn't do anything. It would just, stay there, and you wouldn't have any quick rusting because it would just block it from rusting more. Okay, so the iron is actually going to travel until it reaches the surface where there's going to be oxygen. And so at the cathodic area, your iron 2 plus is going to combine with O2, making iron oxide. And that's rust. And that gives you that sort of reddish color, reddish brown color. So this right here is your anode reaction, which is Fe going to Fe2 plus. And that's solid iron right there, Fe. This right here is going to be your cathodic reaction, which is the oxygen taking on electrons, making hydroxide. And this will combine with then your iron and hydroxide will then combine together to make an insoluble rust, iron oxide. So how can you prevent corrosion? Well, an application of paint or metal plating will help. If you paint or plate metal over this, that is more resistant to corrosion. This will keep the water from coming in contact. This will keep the oxygen from coming in contact. And this will keep any of the iron that does happen to rust from, going anywhere. Galvanizing. This is a process in which steel is coated with zinc to prevent corrosion. Now, notice that these are all fairly temporary measures, okay? So, galvanizing, painting, plating, all of those are relatively temporary. If you use those as outdoor, like screws, for example, they will rust after a few years. You'll start getting a little bit of rust, and it will run down, and you'll notice it, okay? I did that once, and it was not great. Alloying. This is how you get things like stainless steel, okay? And so, yes, you can get stainless steel. Some stainless steels are actually extremely resistant to rusting and corrosion. Cathodic protection. This is actually the major way you typically protect steel in things that use a lot of steel, okay? So alloying makes, you can make very, very good stainless steel that does not corrode very easily, but you would not want to make something like a fuel tank or a pipeline out of it. It would be incredibly expensive. If you have to, sure. A lot of water mains are made with this, with plating of, with a surface of rubberization agent over the top of it. By the way, that's how I got through undergraduate. I laid pipe down in near Vegas in 140 degree heat. Water mains, man, that sucked. Anyways, so cathodic protection. This is going to protect your steel and things like buried fuel tanks, pipelines, that sort of thing. And this right here is your cathodic protection. So you have your tank, your pipeline, whatever. And what you'll do is you'll connect it to an insulating wire. And that will give you a more easily corroded metal at the end of it. Therefore, instead of your steel acting as your anode, that more easily corroded metal will act as your anode. Typically, you use a little piece of magnesium. Um, and so this will slowly corrode. It'll act as your anode. You'll lose the magnesium. You won't lose any of the iron. That will stay complete as a pipe or tank or whatever. Your electrolyte is actually your moist soil, if you're curious. This is one of the reasons you always have to do some sort of cathodic protection or something, is your electrolyte is in contact all over your cathode right here, which is that buried object, because soil typically picks up some degree of moisture, which is called your groundwater. So why is aluminum protected from corrosion? Well, the standard reduction potential for aluminum 3 plus is 1.66 volts. The aluminum forms your protective oxide coating, doesn't it? The aluminum itself will quite readily be oxidized if it doesn't have anything to protect it. But luckily it forms a protective coating, the aluminum oxide, that will prevent it from further corrosion. Excuse me, let me get a drink. All right, electrolysis. This is actually, there's a bunch of reasons that this is important. The major reason is you may have heard something about making hydrogen for hydrogen fuel cells. You can also use this for a variety of different purposes for making various different compounds. But one of the things that I find the most interesting about this is actually a very common garage experiment people do. I've met dozens of people over my career that do this in their garage, make hydrogen balloons and stuff, make their own hydrogen fuel for various purposes. And you can actually, it makes a very loud, very impressive looking explosion, but doesn't really do any damage. Maybe to your ears, but. So, electrolysis is forcing a current through a cell to produce a chemical change for which the cell potential is negative. So you're going to move the reaction in the non-spontaneous direction against what it would be spontaneous in. So that you can either plate out the metal where you want it, you could produce hydrogen gas, you can do quite a variety of things with this, of course. An electrolytic cell, this is going to be a device that uses electrical energy to produce a chemical change. This is pretty common in making things like aluminum metal, copper metal. That's one of the places you typically find these. So right here we see a normal galvanic cell, and so the potential actually moves electrons in the anode to cathode direction, and we don't have to worry about it. It's spontaneous, right? Okay, so an electrolytic cell, we're going to use an external power source. We're going to force these electrons to move in the opposite direction. We're going to push them uphill, if you will. We're going to move them against their normal electromotive force. This power source will have to be greater than 1.1 volts. Why is that? Well, because that's the downward EMF. That is the potential we have to overcome. So we have to overcome the 1.1 volts to move the electrons in the opposite direction. Now, again, this has to be greater. If these are equal, 1.1 volts, if you just do 1.1 volts for your power source here, nothing will happen. This will actually just be at equilibrium. So you won't have anything actually occur. So stoichiometry of electrolysis, you can actually use this in a laboratory setting to determine the stoichiometry of a reaction. So this is going to refer to determining how much chemical change occurs with the flow of a given current for a specified time. Your steps to solve a stoichiometry problem are going to be the current and time. That will go on to give you the quantity of charge in coulombs. Because again, the current actually measures how much electrons are moved, which will give you quantity of charge in coulombs. This will give you your moles of electrons from that, because this is a more easily measured value. This will give you then, well, moles of electrons you may have remembered from your reduction reactions. For example, we added one electron and we get one copper metal, right? Well, that means that would be a 1-to-1 ratio between moles of electrons and moles of copper. And so this is a direct stoichiometric ratio based on that reduction reaction. This moles of copper can also then give you grams. And hopefully you remember how to do this, step 4, because that's just molar mass, isn't it? Okay, let's try this out. So how long must a current of 5 ampere be applied to a solution of Ag plus to produce 10.5 grams silver metal? Okay, in this case, we must use the steps that we've given earlier in reverse. We're doing this backwards. So we have the amount, right, the grams of silver. We're going to get that into moles. And so we will use the molar mass of silver from the periodic table, and we will divide that 10.5 grams by that molar mass. And that will give us moles of silver. So each silver Ag plus ion, well, it's Ag plus, so to become neutral, which would be our metal form, we will have to gain one electron, won't we? So each Ag plus ion will need one electron. Thus, we'll need to use 9.73 times 10 to the negative 2 moles of electrons would give you that 10 grams, 10.5 grams of silver, solid silver. All right, so the next thing we have to do is we have to calculate out the coulombs, the charge, so we can get into amps. So right here, we see this is 9.73 times 10 to the negative 2 moles of electrons. Well, we know the relationship between coulombs and moles of electrons. That's that Faraday, right? And so we multiply that by 96,000 right here. And that will give us 9.39 times 10 to the third coulomb. All right. So an ampere is a coulomb per second. So the 5 ampere of current must produce 9.39 times 10 to the third coulombs of charge. And so we take that 5 coulomb per second, that'll be times time in seconds, will equal our number of coulombs. So we take this number, we divide it by that 5 right there, that will give us our time in seconds. Now, you may want to do that in minutes instead, a little easier to deal with. So you divide by 60, you get your minutes. And there you go. That is your problem. Okay, so this is the electrolysis of water, and this is a non-spontaneous reaction again. We would have to provide an external energy source to push this reaction along. And this just shows you the reaction. Right here is your anode reaction, right here's your cathode reaction. Notice you're producing hydrogen gas here at your cathode. And so your overall E naught is a -2. That means you have to provide energy to push this in the non-spontaneous direction. So let's go ahead and do an interactive example so we can further refine our math skills here. An acidic solution contains ions Ce4+, VO2+, and Fe3+. Use the E naught values in table 18.1, which is that table I showed you before. Give the order of oxidizing ability of these species and predict which one will be reduced at the cathode of an electrolytic cell at the lowest voltage. So your half reactions and E naught values are these right here off of that table. And again, these are reduction reactions and E naught values. The order of oxidizing ability therefore has to be Ce4 plus is your greatest one, because it's going to most easily take on electrons because it has the largest potential. VO2 plus is your next because it has the next largest, and Fe3 plus is your least oxidizing ability because it's the smallest value. So your Ce4 plus, this is going to be reduced at the lowest voltage in an electrolytic cell. That's going to take the electrons first. That's going to take the electrons most easily. That's going to become reduced the most easily. All right, so let's go ahead and talk about production of aluminum. There's a little bit of a fascinating thing that is a side note that sort of is a little bit of a commentary on the EU also, but okay, so bauxite, one of the major sources of bauxite, which is the mineral that you can extract aluminum from, is Greece. Greece is an incredibly poor country, very, very mineral rich though. And the reason it's poor, even though aluminum is a huge, very expensive metal, very huge amount of it is needed every year, you would think that Greeks would be fairly rich because they, have the source of bauxite. But they make very little from the sale of the bauxite. They sell it to France because France has all the nuclear power generators and all the facilities to make the aluminum from bauxite. And France is quite wealthy. So this is a case of, the EU tax credits, carbon swap credits, and the technology for nuclear power not being made available has sort of just screwed over Greece and made all of what should have probably been their wealth into France's wealth. It's not really that funny, but it's actually kind of sad. But anyways, it's a kind of interesting side note that you really wouldn't understand until this chapter right here, right? So this bauxite that you extract aluminum from, this is not pure aluminum oxide. The bauxite is treated with aqueous sodium hydroxide to obtain pure hydrated alumina, which, by the way, is ironically actually is done in Greece because it produces nasty byproducts. Anyways, the alumina dissolves in basic solution. You may have actually done a similar reaction to this. Many people end up doing that, a similar reaction to this in their labs in General Chemistry 1 or 2. So the other metals will remain as solids and be left behind. The extraction of the purified alumina is this reaction right here. And this right here is your purified alumina. Oh, I got a funny story after this. I'll go ahead and tell you. Just because I guess I'm just telling stories tonight. So purified alumina is going to be mixed with your cryolite, and that'll be melted. So the aluminum ion is then going to be reduced to aluminum metal in an electrolytic cell. And this takes a lot of energy and power. Really, the only people that can do it are going to be people that use nuclear facilities to do so, because it just takes so much energy. You would have to replace your entire country with solar panels if you want to do that. It's not practical to do it using coal. Typically, you can only find these sort of facilities next to a nuclear power plant. So alumina reacts with the cryolite anion, like so. The overall cell reaction is thus this right here. And so the aluminum produced from this is 99.5% pure. And this is actually pretty common for most electrolytic cells. So electrolytic processes, one of the great things about them is they just produce the most pure metals you can get. Okay, they produce 99.5% purity almost across the board. Really, I have never actually seen an electrolytic cell that was run even remotely decently that didn't produce 99+% purities. Okay, I'm gonna go ahead and tell a story here since I might as well, right? Let's have a little fun with it. So, you guys have all probably heard of Napoleon Bonaparte, you know, emperor, famous conqueror, uh, kind of short guy. he he one of his famous things is he was the emperor of France, and he was actually for a while people thought he'd be the emperor of all Europe. He was very, very powerful and influential in his day. And so he would have dinner with various different peoples and dignitaries. And when he wanted to when he was having dinner with an officer of his, he might bring out silverware, just silverware made out of silver, right? Just like we do. If he wanted to impress you a little bit, he might bring out, gold. If he's dining, a king or something that he doesn't think is that important and he doesn't need to impress that much, he might bring out, ruby and sapphire encrusted gold plates and silverware. So when he really wanted to impress somebody and wanted them to go, my God, he has this much wealth, I can't even begin to compare, he would bring out aluminum plates and silverware. Because in the day, he owned something like 90% of the aluminum on the planet. And that was only enough to make a set of eating utensils. Because back in that day, he did not have cheap and easy to get electricity. And so you could not do this process cheaply and easily. Also, they didn't know these previous processes, so this was even more energy intensive back then. Anyways, that's kind of a funny, interesting side story to aluminum, if you're curious. Alright, so right here we see the schematic diagram of an electrolytic cell for producing aluminum by the Hall-Héroult process. Hall-Héroult process. Excuse me, I don't know why I keep mispronouncing everything tonight. Alright, anyways, this diagram right here, it shows you the molten aluminum oxide with this mixture here. You have this attached to an external power source. Here you have your electrodes of graphite rods that will produce this carbon dioxide that will be formed at your anodes, which will leak out. Uh, this is going to be a carbon-lined iron tank where the molten aluminum will collect, which you can then empty out like so. You would, of course, replug this in before this part drains. This happens at fairly high temperatures, by the way, which is part of what makes this fairly energy intensive, though this is much, much more efficient than just pure electrolysis that you might have been thinking about. Okay, so a solution in an electrolytic cell contains ions copper 2 plus, iron 2 plus, zinc 2 plus. If the voltage, initially very low, is turned up, in which order will the metals be plated out onto the cathode? Okay, so what you're looking for here is obviously um, this is going to be plating out the metals, so we already have the reactions in the correct directions. So this is going to happen first, right? Then this. And so you would expect copper, iron, then zinc. Again, copper, iron, zinc. It's due to the fact that this is positive. This doesn't even need voltage to be applied to it, though you can make it faster. This right here will need 0.44 volts to be applied or greater to make this occur. The greater voltage you apply, the faster this will happen. This right here will need 0.76 volts or greater to be applied. So you'd plate this out first. This actually should be plating out without anything. This right here would then start plating out, and then you'd start plating this one out. So electrorefining of metals. Impure copper that is derived from the reduction of copper ore is cast into large slabs that serve as anodes for electrolytic cells. So electrolyte will be aqueous copper sulfate. The cathodes will be thin sheets of ultra pure copper. And so this right here is your anode reaction. This right here is your cathode reaction. And so right here we see metal plating next. This protects metals that corrode easily. This is things like silver plated or chrome plated, nickel plated. That's all of these things, okay? This can be easily done by making an object as the cathode in your tank. So literally you just take like a spoon, silver plated spoon, and you take that steel or whatever spoon, and you would go ahead and just use a power source to take a lump of silver and transfer electrons through to cause these silver ions to collect on your spoon. And you see that transfer of electrons is going to cause the silver solid to go to the silver ions in that solution and the electrolyte, and then collect up on this surface. By the way, this typically requires some sort of buffing afterwards, because this will not be a very even surface usually. So anyways, this is an electroplating right here. You can use this in a single container. You usually do this entire process in a single container. This is how they usually make like chrome bumpers, everything else. I mean, you get the idea. Electrolysis of sodium chloride, brine. So this process is used for the production of sodium metal. And so the steps is going to be mix solid NaCl. Oh, by the way, I know I'm going to show you brine sodium metal, but one of the major sources you can get most metals from is actually the ocean. The ocean has a tremendous amount of metals dissolved into it. And so you can get like gold from it, you can get all sorts of things. Though it's not very efficient, it's much more efficient just to mine the ore than it is to plate the metal out of the ocean. So this is the process used for production of sodium metal, of course. Steps, you mix the sodium NaCl, the solid NaCl, with solid calcium chloride. This will lower its melting point. The electrolyze the mixture in a down cell. And this right here will be your anode reaction. This right here will be your cathode reaction. You may have been going, what the heck's a down cell? Well, there's your down cell. You don't need to know a whole lot about this, honestly. I just thought you may be somewhat interested, honestly. It's just something, you can get something out of. Alright, so the sodium is going to be drained off in the down cell. This will be cooled and cast into blocks. This is stored in an inert solvent. You need typically something like a mineral oil because sodium is very reactive to the moisture in the air. And this will prevent its oxidation by the air. This is going to produce hydrogen and chlorine gas, which, if you can collect them up, actually are useful things, but would normally not be something you want to have leaking out into your lab or some suchness. This leaves a solution containing dissolved NaOH and NaCl. Okay, so the mercury cell for production of chlorine and sodium hydroxide. Contamination of the sodium hydroxide by NaCl. This can actually be eliminated by electrolyzing the brine in a mercury cell, which is what we're seeing right here. The reaction of the insulating sodium metal is this reaction right here. The chlor-alkali process, this is going to involve recovering the pure NaOH from your aqueous solution. And keep in mind that sodium hydroxide is not exactly cheap. So typically in an industrial setting, you do not want to dump away this sort of stuff. It's much more cost effective to recover. Also, the environmental damage from dumping NaOH would be horrible. You'd make soap out of everything you dump it on. Every biological organism you dump it on, at least. Pumping the regenerated mercury into the electrolysis cell. This is currently carried out in diaphragm cells. The cathode and anode are separated by a diaphragm. That's where this name comes from, diaphragm cells. This allows passage of the water molecules, the sodium ions, and the chloride ions. This will block your passage of the hydroxide ions, though. So what are the disadvantages? Well, Your aqueous effluent from the cathode compartment contains a mixture of NaOH and untreated NaCl. So this needs to be purified to derive your pure NaOH. There's an advancement in the chlor-alkali industry. So this uses a membrane to separate the anode and cathode compartments in the brine electrolysis cells. This membrane is impermeable to the anions, and so it makes it a little bit easier to purify, to separate these components. Okay, that's it. You folks take care. Have a great time. And I will get the next one out tomorrow sometime.